Hello everyone, welcome to series lectures of Basic Electronics. I am Heming Sathwara and working in LG Institute of Engineering and Technology. So today we are going to discuss about C configuration and its characteristics. So don't waste time, let us start this topic. So here we have seen various types of operations, cutoff, saturation and active. In this today's topic we are going to discuss about active region, because if in order to use transistor as an amplifier, it should be in operated active region. Active region, that means your base emitter junction should be in forward biased and your collector base junction should be in reverse bias. So let us discuss about common configurations. So here we can see this is the transistor configurations, which is also known as common configurations. Common configurations, that means there are three types of terminals. If you that particular terminal put on common, that becomes common configuration. For example, I take emitter terminal as a common, so that means it becomes common emitter configuration. If I consider base as a common, that becomes common base configuration. If I take collector as a common, that becomes common collector configurations. So in this lecture we are going to discuss about C configuration only. So let us discuss about C configuration. So we are going to discuss about C configuration, that means common emitter configuration. So we should take here emitter as a common terminal. So here in this circuit diagram we can see emitter terminal becomes common. That means your base and collector terminal is open for the input or output. Here as an input terminal we are using base terminal, and as an output terminal we are using collector terminal. Now here we can see VBB. This is your input voltage, or we can see VBE. That means potential difference between base and emitter becomes VBE. That is your input voltage. So it is in forward biased. Why it is forward biased? Why we can say it is forward biased? Here VBB's first polarity is positive plus, which is directly connected to the NPN's P region. That means P means positive, and here VBB's first polarity is positive. So this is similar, that becomes forward region. Now here VCC is your output voltage, or we can say VCE is your output voltage. VCC is your reverse bias. Why it is known as reverse bias? Here we can see VCC's first polarity is positive, which is directly connected to the NPN's N region. That means N, or here positive. That means it is similar. It becomes reverse bias. So that's why here we are going to connect VBB as a forward bias and here VCC as a reverse bias. Now let us discuss about its characteristics. There are two types of characteristics. One is input characteristics and output characteristics. First we are going to learn about input characteristics. Here we can see input characteristics is basically VI characteristics as we discussed in a PN junction diode. This is the voltage versus current graph, but it is particularly input characteristic. That means we have to take here input voltage and input current with values of output voltage. Here we can see this is the plot of input current, which is IB, that means base current, versus input voltage, that is VBE, base to emitter voltage with constant output voltage VCE. So here on the x-axis we are going to take VBE, which is in volts, and at y-axis we are going to take IB, which is in microampere. So here you can imagine your graph like this. At VCE is equal to 0 voltage, your graph is like this. Why? Because this is the basically in forward bias. This is in forward region. That's why your characteristics is like forward region. Here we can see this is the PN junction diode's VI characteristics basically. So here VCE is equal to 0 volt, your graph should be like this. If we are going to increase VCE's value, then your graph should be like this. VCE is equal to 10 volt, VCE is equal to 20 volt. Now at fixed values of VBE, here we can see at constant VBE at this point, your IB's value is different. First we are going to take VCE is equal to 0 volt. At this time your IB is like this, 60 microampere. If your VCE's value is equal to 10 volt, then your IB's value is equal to 40 microampere. If your VCE is equal to 20 volt, then your IB is equal to 20 microampere. So that means if we increase VCE's value, then your IB's value is going to be decreased. First VCE is equal to 0, at that time your IB's is equal to 60 microampere, then you increased VCE is equal to 10 volt, then it becomes 40 microampere, and last VCE is equal to 20 volt, then your IB's value is equal to 20 microampere. So why it happens? Because VCE is in reverse bias. If you increase the reverse voltage, that means the depletion region width is increased. That's why your base region's electric width is going to be decreased. And that's why the recombination process is going to be decreased. And if your recombination process is going to decrease, that means your base current, that means IB, is also reduced. That's why your VCE is equal to 0, 10, 20, and your IB becomes 60 microampere to 20 microampere. So this is the input characteristics of C configuration. Now let us discuss about output characteristics. Now here output characteristics, this is the same like input characteristics, but here we have to take output voltage, output current with different values of input current, that is IB. So here this is the plot of output current IC versus output voltage VCE with input current IB. Here at x-axis we can see VCE, which is in volts, and y-axis we can see IC, which is in milliampere. Now here we are going to divide this characteristics into three parts. First one is cutoff region. Now what is cutoff region? At this time your IB is equal to 0. If your IB is equal to 0, then your leakage current becomes your collector current, because your input current is equal to 0, that means your leakage current becomes your output current IC. So here we can see at this region IB is equal to 0 microampere. Below this graph we can see the cutoff region. So here we can see this is the cutoff region. Now second, active region. Active region, that means your BE junction should be in forward biased and your CB junction is in reverse bias. That means this is the active region. But here we can see at the fixed value of VCE, here IB is equal to 10 volt. If you change base current's value, then you will get different values of IC. Here we can see IB is equal to 10 microampere. At this time your IC is different. That means we can say your IC is equal to 1 milliampere. Here IB is equal to 20 microampere. At this time your IC is equal to 2 milliampere. If you change your IB, again IB is equal to 30 microampere, then your IC is equal to 3 milliampere. And your IB is equal to 40 microampere. At this time your IC is equal to 4 milliampere. That means here we can conclude about this graph with the help of this equation. We know about the equation IC is equal to beta into IB. So it depends on beta. You will get your output signal. So this region is known as active region. And finally, let us discuss about saturation region. In saturation region, your both junctions should be in forward biased. So your saturation region is like this. So this is your saturation region. Here we can see this is your active region. So this is the reverse resistance. How can we find reverse resistance? It is due to the voltage and current. So resistance is equal to the ratio of voltage VCE upon IC, and IC is equal to beta into IB. Now transistor current gains. Here we can see current gain is equal to output upon input. Gain, that means it is the ratio of output upon input. This is the CB current gain, that means common base current gain is equal to alpha. CE current gain, as we discussed in our previous equation, IC is equal to beta into IB. So its gain is beta. And CC current gain, common collector current gain, is equal to gamma. Here alpha is equal to IC upon IE, beta is equal to IC upon IB, and gamma is equal to IE upon IB. So here we can discuss only CE current gain, common emitter current gain, that is beta. Beta is equal to IC upon IB. So we know about this basic equation as we discussed in our introduction of BJT, that IE is equal to IB plus IC, whereas IB is only 2% of total current and IC is 98% of total current. So let us discuss about relation between the current gains alpha and beta. So we know about this equation. This is the equation number 1. IE is equal to IB plus IC. Beta is equal to IC upon IB. This is the current gain. This is equation number 2. Here IB is equal to IE minus IC. From this equation number 1, we take IB as a common. So this equation will be IB is equal to IE minus IC. Now put this equation into equation number 2. So it becomes beta is equal to IC upon IE minus IC. Now we have to prove here alpha and beta relationship. So beta is already there as a subject, but we have to take left hand side alpha. So we have to divide by IE. So divide by IE in numerator and denominator in equation number 3. So it is like this: beta is equal to IC upon IE, divide by IE upon IE minus IC upon IE. Now here we can see IE upon IE, that becomes 1, and here IC upon IE, that means it is alpha. So we can put here IC upon IE is equal to alpha. So your equation will be beta is equal to alpha upon 1 minus alpha. So this is the one of the relation between the alpha and beta. Now we have to prove alpha is equal to beta in bracket 1 minus alpha. Here we common alpha, or we can say we subject as a alpha. So beta into 1 minus alpha. Now multiply beta inside the equation, so it becomes alpha is equal to beta minus beta into alpha. Now here beta alpha goes with the alpha, that means alpha plus beta alpha is equal to beta. So from this equation we can common alpha, so it becomes alpha in bracket 1 plus beta is equal to beta. So we can write here alpha is equal to beta upon 1 plus beta. So this is the second relationship between the alpha and beta. So today we discussed about C configuration and its characteristics. So that's all for today's lecture. If you have any questions related to this topic, you can mail me on this email address. Till then, keep reading, keep learning. See you soon in next coming lectures. Thank you.